So last time we started defining complexity classes to capture counting, right? So the primary counting problem is sharp-sat, which is a functional problem. So it takes a Boolean formula and it outputs how many satisfying assignments there are of this Boolean formula phi. And to capture efficiency in efficient functional problems, we define the class FP, which is a collection of functions f that are computable by polytime Turing machines. And the open question is sharp-sat is not in efficiently solvable functions. So this class defines its own, this problem defines its own complexity class sharp P. So that is those functions which have a Turing machine whose kind of number of accepting paths they count. Okay, so if you think of m x comma y as a NDTM and y as as an accepting path, so how many accepting paths are there? Number of y's. That is what f of x computes. So this sharp-sat is in sharp P and it is supposed to be a hard problem. So sharp P is supposed to be a class harder than that, harder than NP. It clearly contains FP, and given that you can solve NP, and you can solve itself in P space. In the same space you can do counting. So let us now move to a new class that comes out of sharp P. So sharp P has an analogous decision version. Which is PP. So language L in PP, language L will be put in the class PP if there exists a polytime Turing machine M and constant C such that for all x, for all input x, x is in L if and only if the number of accepting paths such that mxy is 1. So PP stands for probabilistic polynomial time, and what will happen here is the number of accepting paths will be more than half, or at least half. Okay, so amongst the paths, at least half of them are accepting. When that happens, then we say, then X is a yes string. Okay, if and only if. So such problems which are solvable by this, you can think of it as a, for now, as a probabilistic Turing machine. With probability half it accepts, and less than half it rejects. So there is a minuscule advantage that it is giving to the yes string, which is half. So function in PP computes the most significant bit of the corresponding function in sharp P. Okay, that's the first observation we can make, that a Boolean function in PP, let me add Boolean here, that's important. So Boolean function, for example, this language L, this is in PP, so it means that you are able to compute the most significant bit, right? So basically, if you see in binary the number of accepting paths, then the most significant bit is 1 if half of the paths are accepting, otherwise it is 0, and that is what defines PP. So we will now prove some interesting facts, that actually PP and Sharpie are in a way equivalent. So what we will show is sharp sat. Sharp sat can be solved using PP as an oracle. Okay, so if you can compute the most significant bit, then using that as a subroutine, you can actually compute the whole string, giving you the count of accepting paths. Okay, that's an interesting consequence, and hence it would imply that if you can compute Sharpie, then using that oracle, like SharpSat oracle, you can solve PP. Okay, so to a polynomial time machine, Sharpie oracle is equivalent to PP oracle. Okay, so in that sense, PP and Sharpie are kind of equivalent. Okay, there is a kind of equivalence in computing the most significant bit and the whole string of the count. So the key thing is to show the first property, which is how do you compute the number of satisfying assignments if you know that the satisfying assignments are at least half. So let phi be a Boolean formula given in the input in variables x1 to xn. So using PP, we know if the number of satisfying assignments of phi, okay, this notation will mean number of satisfying assignments. Is greater than equal to 2 raised to n minus 1 or not. Okay, so we will be basically able to compute the MSB of number of satisfying assignments. So since it's in n variables, half is 2 raised to n minus 1. But then from this, how do we actually compute this sharp phi? This is just one bit. How do we compute the other bits? Somehow we have to fill this difference, right? This unknown difference between 2 raised to n minus 1 and sharp phi. So for that, let us define the difference as k. So the idea is to find the minimum non-negative integer k such that k plus k plus number of satisfying assignments is 2 raised to n, at least 2 raised to n, right? So greater than equal to, but since we are saying minimum k, it's actually an equality using binary search and n plus 1 non-deterministic bits. Okay, so we'll compute the difference using binary search and many non-deterministic bits. So with that, what we would have shown is that using PP, we have solved sharp set in deterministic polynomial time. Okay, base machine has to be FP. So consider NDTM M that on input phi and k uses non-deterministic bits y0 to yn as follows. So on y0 equal to 1, M guesses y these n bits, it makes this guess and outputs phi y bar. So basically on it is just guessing a satisfying assignment, right? It will be 1, output will be 1 if and only if a satisfying assignment was guessed. Otherwise, so this is kind of point number 1 or step 1 is the part of hash phi, right? You can think of this as step 1. And the step 2 will be corresponding to k, and so that the sum comes out to be 2 raised to n. So on y0 equal to 0, M accepts exactly k strings y bar. That's the k part, right? So y0 equal to 1 is covering hash phi, and y0 equal to 0 is covering k, and so total number of accepting paths is by definition 2 raised to n. So let's write that down. So number of accepting paths of M phi k is k plus this is by definition the way it is accepting, right? While the possible paths this is exactly all possible values of y0 to yn, which is 2 raised to n plus 1, right? So so we have basically made 2 raised to n half of 2 raised to n plus 1. Okay, in this, by this orange definition, we have an NDTM where if the number of accepting paths is half or more, that will be enough to compute k. So, but you have to start with a k. So, basically the idea is that you guess k and then verify it by using PP oracle, okay, to do a binary search, and by that in around n iterations you will be able to find the right value of k. So, k plus the number of assignments satisfying assignments greater than or equal to 2 raised to n. This can be learnt by querying the PP oracle on phi k. Okay, so you can start with k, let's say 1, check this by PP oracle. If this is false, then it means that you should increase k, so double k, which is 2. If this also fails, then you go to 4, k equal to 4, and so on. So find k min so starting with k to be 1, then 2, then 4, then 8, and ultimately k maximum can be 2 raised to n. Right? Try all these n plus 1 possibilities. So find k min from MSB to LSB bit by bit, each using a query to PP oracle. So in n plus 1 calls, in at most n plus 1 calls to the oracle, we find k min, and so it means that we have computed the number of satisfying assignments. Right. So once we find k min, then the difference gives us the number of satisfying assignments. So that is, this is just an FP computation, right, with n plus 1 oracle calls to a PP problem, like the hardest problem in PP. So if you can solve PP, then you can solve sharp set. Thus, sharp sat is in FP to the PP. So that's a nice reduction from sharps of PP to sharp set to PP. And the second proposition is now immediate. Okay, so how do you do that? Let's solve that. So we have already shown that p raised to sharp sat is contained in p raised to pp. Right? If you can solve pp, then making those calls you can solve sharp sat. And so any problem that is calling sharp sat as an oracle, those calls can be replaced by pp oracle calls. So p raised to sharp sat is in p raised to pp. And but you wanted to show an equality. In fact, the same proof shows that for any problem in sharp p, p raised to L is in p raised to pp. Well, this is because we didn't really use sharp sat's specific properties. Right? You can do the same thing with any problem in sharp p. So for any sharp p problem L, p raised to L is in p raised to pp. And what does this mean? This actually implies that p raised to sharp p is in p raised to pp. Okay, every call can be replaced by a pp oracle call. So we have shown both ways. While p raised to pp is trivially in p raised to sharp p. Okay, p raised to pp is in p raised to sharp p because, well, if you have sharp p access, you have access to all the bits of the count. So you obviously can also compute the most significant bit. So that is trivial, which means that p raised to pp is p raised to sharp p. Okay, so that finishes this equivalence. So again, we started with functional complexity class sharp p. We ended up showing that it's actually equivalent to a decision, to a normal complexity class, which is pp. And now we will investigate sharp p further. Okay, sharp p actually has complete problems, so let's investigate them. So call function f sharp p complete if, first of all, it should be in sharp p itself, and every problem in sharp p should reduce to this function. So sharp p should be in fp given f. Okay, so this is a nice way to say that every problem in sharp p reduces to f. Basically, sharp p should be a subset of functional, efficiently solvable functional problems using f as an oracle. So this is called sharp p hard. So what this is saying is that f is sharp p hard. If it is also in p sharp p, then it becomes sharp p complete. This thing, by the way, is also called Turing reduction. So this is also the notion of Turing reduction. Okay, in contrast to the KARP reduction we saw. So here actually subroutine calls are being made. So whatever you can solve by calling f as a subroutine, so there will be many calls possibly, polynomially many calls. So if using this, if you can solve a problem G, then you call it a Turing reduction from G to F. Suppose G is here. Then notion of Turing reduction of G to F. Okay, this is much more powerful than KARP reduction. Now from this reduction or the completeness notion, sharp P completeness, what you can see trivially is if a sharp P complete problem is in FP, so F is sharp P complete and F is in FP, then FP is sharp P. Because if you can already solve F in functional polynomial time, then functional polynomial time, calling functional polynomial time as an oracle is still functional polynomial time. Okay, so just because of that, sharp P will be inside FP. That's the simple proof. And what is a sharp P complete problem? Is there a natural problem that is sharp P complete? So we have been looking at sharp SAT, and that happens to be sharp P complete. Follows from Cook-Levin directly. So sharp SAT is sharp P complete. So we know that sharp SAT is in sharp P, and now we have to show that it is also sharp P hard. So every problem in sharp P should reduce to this in the above sense, right? Turing sense. Well, let G be in sharp P with corresponding so G is computing number of accepting paths of a NDTM M. So since M's computation can be converted to a Boolean formula, okay, M's computation can be converted to a Boolean formula by Cook-Levin. So what it means is that for all input x, this g of x is equal to number of accepting paths of M on X, which is also equal to so let me call the Boolean formula phi which is also equal to the number of satisfying assignments. Right, which implies that G is in FP to the sharp set. So think of Cook-Levin reduction as a efficient function, which it is. It was just quadratic blow up, and then you can make a sharp set call. Right, and once you have the sharp set call, you will know the value G of X. So this, since G was anything in sharp P, it means that sharp P as a whole is in FP to the sharp set. And now, so that's hardness. Right? Sharp set is sharp P hard, and hence it is complete. Yeah, so that gives a pretty good understanding of sharp P. We have a complete problem of sharp P. We have a Boolean version of sharp P. And what we'll do next is something even more brilliant, which is an algebraic formulation of sharp P. Okay.